The next extension 2 topic, as you can see, is polynomials, but there really is a huge crossover with complex numbers and polynomials. I mean, as you saw in the complex number topics, we were factorising and finding roots and things like that, which is very much a polynomial thing as well. So the first thing we look at, again, is a bit of a crossover, factorising those complex expressions. So sort of is a bit of a recap of what we've seen already. But this was one of the key ideas that we did see, that if the coefficients are all real, then we know that the roots will appear in conjugate pairs, and that can help us factorise. So all polynomials can be factorised as a combination of quadratics and linear. If it is a complex root, then you get it and its conjugate, and that'll create the quadratic root. So if we were just using real numbers and we have a quadratic that can't be factorised, well, we just stop there. That's the best we can do using real numbers. If we were to factorise it over the complex field, then they would all be linear factors, because one factor would be x minus whatever that imaginary number is. So we could break it down to n linear factors. So what that therefore means is any odd-ordered polynomial must have at least one real root. Because if the imaginary ones are appearing in pairs, they will all end up being an even number. Which means if it's odd, then it must leave at least one real solution. X squared plus 2x plus 2. Ooh, that's a tricky one to start off with. Now, of course, we see this and we'd say, oh, what multiplies together to give 2, adds together to give 2. And we can struggle and go, 2 times 1. How can I make that add together to give 2? Well, you can't, obviously. So this one is one that will have complex roots. I'm going to do it by completing the square. If I complete the square on that, I'd get x plus 1 all squared. But when I expand that out, I'd get positive 1. I want positive 2. And so it's plus 1. Now that caused us problems until we saw the idea that I squared is negative 1. Because that now means I can rewrite that as, instead of plus 1, that's what I'm seeing, but what I'm actually thinking is minus I squared. So it becomes the difference of two squares, x plus 1 plus I, x plus 1 minus I. Ooh, z to the 4 plus z squared minus 12 equals 0. Well, that does factorise like a quadratic, even though it's a quartic. Adds together to give minus 12, adds together to give 1, so I've got 4 and minus 3. Now, the square root of 3 is the square root of 3. No? Strange statement, I suppose. But it is the difference of two squares, I guess, is what I'm getting at there. So I could write it as z plus root 3 over z minus root 3. Now, if they want real solutions, then the z squared plus 4 I can't do anything with, of course. So over real numbers, that would be it factorised, and I would solve it. And using just real numbers, I would only have the solutions plus or minus root 3. But if we now include the imaginary numbers, I can now factorise the z squared plus 4. I'll get plus 2i minus 2i. And then my final solutions, therefore, plus or minus root 3, plus or minus 2i. Just a reminder of our factor theorem. If x minus a is a factor, then we know polynomial a will equal 0. So I'm searching for factors. I just substitute numbers into the polynomial. If the answer is 0, then I know x minus that number is a factor. If it's not monic, then I might have a factor ax minus b. And so then I would try things like b over a. So some fraction where the top of the fraction goes into the constant and the bottom of the fraction goes into the leading coefficient. So this one here, 2x cubed minus 3x squared plus 8x plus 5. They want me to factorise it, but the first thing I notice is it's a cubic. A cubic is an odd number. Therefore, I know a real solution does exist. So I'm going to search for that. Now, fortunately, I've used some prime numbers there. Make life a little bit easier. So I'm looking at 5, a possibility. Minus 5 could be a possibility. 1, minus 1. But it's not monic, so I could also have those numbers over 2 as well. So it might be 5 over 2, minus 5 over 2. A half minus a half. So logically, the first one you would try amongst all those numbers would be what? 1 you would think would be logical, because that's an easy number to substitute in, but I didn't do that. I used a minus a half. Clearly a logical one to pick first. Oh, look, it turned out to be 0. How lucky was that, hey? So polynomial minus a half turns out to be 0. So I now know 2x plus 1 is a factor. I can do a polynomial division, or I can look it up by inspection to work out the second factor. It turns out to be x squared minus 2x plus 5. Multiplies together to give 5, adds together to give minus 2. No, that doesn't work, does it? So if I'm just factorising over the real numbers, I would stop there. Complex numbers, no, that's not absolute value. For some reason, the top of my brackets got knocked off there. So it's x minus 1 squared if I'm completing the square, plus 4. So I get x minus 1 minus 2i, x minus 1 plus 2i. A quartic. But they have told me there are 2 rational zeros. Now, if they're rational, so that straight away tells me they're real. So when we're looking at the family of numbers, imaginary numbers didn't have things like real, irrational, and so on. They all belonged in the real numbers. So if they've told me there's rational ones, I know they're real ones, but it also means it's not going to be a surd as well. It's going to be well, not necessarily a whole number. It might be a fraction, because we haven't got a monic one, so it might be a fraction. It wants us to find those and then go and factorise completely, so over the complex field. Okay, so possibilities. 3 again. I'm lucky it's a prime number. So 3 minus 3, 1 minus 1. 4, however, gives me a couple of possibilities, because 4 goes into 4, but so does 2. So what are my possibilities? 3 minus 3, 1 minus 1, a quarter minus a quarter, 3 quarters minus 3 quarters, but I could also have 2 on the bottom, so that leaves me with 3 on 2 minus 3 on 2, minus a half, plus a half, as all our possibilities to try. And once again, logically, you would try a 1. Go for the easy ones first and keep your fingers crossed. Did it work? 4 plus... No, 1's not going to work, is it? Turns out a half does work. So that's one of them. It told me there were 2. So 2x minus 1 is a factor. All right, I could substitute more numbers in, but what I'm going to do is I'm going to try and work out what the cubic is, and that might make life a little bit easier when I'm trying to work out the other factor. So I know leading term times leading term gives me leading term, so it must start with 2x cubed. Constant times constant gives me the constant, so it must end in plus 3. Now at this stage, how many x's have I got? I've got 6x. I want 1x. So to get from 6 to 1, I've got to subtract 5. So it would be minus 1 times 5x. Okay, there the x's sorted out. We've also got x squareds to sort out as well. So let's have a look. How many x squareds have I got at this stage? Yeah, how many did you say? No, you looked at the cubics, didn't you? Now we've got 10 x squareds at this stage. We want 5 x squareds. So to go from 10 to 5, coincidence, but I've got to subtract 5 again. So minus 1 times plus 5x squared. All right, I'm looking for a factor. So I'm going to look for numbers like 3 on 2, minus 3 on 2. Of course, a half might be a double root for all we know. So we should also check those as well. Let's see, what did we get? Minus 3 on 2 turns out to work for this one. Okay, so I now know 2x plus 3 is a factor. So the rational zeros, I know those now. They're a half and minus 3 on 2. Now we need to complete our factorisation. So 2x minus 1, 2x plus 3. The other one then, again, leading term times leading term. I'm just looking at the cubic that we had. So 2x times x squared. Constant times constant would be 3 times positive 1. Again, I'm not looking at the final answer here. I'm looking at the cubic we had in the line before. And when I play around with the other x's, I get... Oh, look there, I do my working out there. plus x, we end up with. Okay, x squared plus x plus 1. It said to factorise completely, didn't it, over the complex field. So I'll complete the square on that one. I get x plus a half squared plus 3/4. Now, avoid the temptation to get rid of those fractions, because it's not an equation. If it was equals 0, then okay, I could multiply both sides by 4 and get rid of those fractions. But it's not an equation. It's saying what equals. When I expand the whole thing out, I've got to get 4x to the power of 4. So at this stage, 2x times 2x already gives me the 4x to the power of something. The other ones have to be x. If you wanted to get rid of these fractions, you could do it. But then in the first ones, I would have to change those. And it would become x minus a half, x plus 3/2. So it looks a bit strange having fractions in there. But that's because I'm dealing with a piece of algebra rather than an equation. And so I can't say, oh, I'll multiply both sides. There's not two sides. There's only one piece of algebra. So we'll leave it like that. All right. Fake Cambridge. Is photocopied at the end of those notes for you. So we'll play with those.